Hello, welcome to this video. We are going to talk about logarithms, a new type of function that is the inverse of exponential functions. And in this video, we're going to go ahead and introduce logarithms and then also kind of show you how they are derived from their inverse exponential functions. All right, so let's go ahead and start off with an exponential function. So a function such as 2 to the power of x accepts values of the exponent as inputs, and then it delivers corresponding values of the power as outputs. Well, the inverse of an exponential function, as I said, is a logarithmic function. Can you say that? Logarithmic function. The inputs of a logarithmic function represent the value of a power, right? So inputs and outputs switch with an inverse function. Okay, the corresponding outputs represent the value of the exponent. Okay, and this makes sense, and I'll show you a diagram. There's also one right behind me here on the board that again kind of shows this relationship. Okay. Now, an important thing to remember about logarithms is that logarithms have bases, and just as exponential functions have bases, okay, and again, we'll dive into that in a second, but for a function 2 to the power of x, the inverse, which is a logarithm, is going to be read as log base 2 of x, and there's a couple of ways you can read this. Again, like I just said, the common way is this: log base 2 of x. Or you could say the logarithm with base 2 of x. But again, the most common one is the latter. Okay? And again, a key concept to remember here that a logarithm is equal to the exponent value. Okay, so let's go ahead and kind of introduce a logarithm and what it is. So here is a graph of 2 to the power of x, and we are asked to graph its inverse on the table. Maybe you're asking yourself, hey, how the heck do I do that? Well, remember, an inverse, inputs and outputs switch. So here, if I have this value here, this is -2, 0.25, and then I have this ordered pair here. This is -1, 0.5, 0, 1. We have 1, 2, 1, 2, and we have 2, 4. Well, if I want to go ahead and graph its inverse, all I'm going to do is I'm going to switch these inputs and outputs. Okay, so I'll go ahead and do this here on the table. So 0.25 is paired with -2. 0.5 is paired with -1. 1, 0, 2, 1, and 4, 2. Oh, I guess I'm missing this one. This is 3, 8 up there, but well, I can add it to the table. Doesn't hurt. Okay, so here is a logarithmic function, and what I'm going to do now is I'm going to go ahead and plot these values. So 0.25 -2 is roughly here. 0.5 -1, 1, 0, 2, 1, 4, 2, and 8, 3. So here is a logarithmic function. Okay, and something that you'll notice about a logarithmic function is that it has a vertical asymptote at x equals 0, so it will never ever touch this this axis. It will never move, right, unless we have translations. Okay, but yeah, so that's what a logarithmic function looks like. Okay. So how do we go ahead and define a logarithm? Well, in general, the exponential function f of x equals b to the x, where b must be a positive value, okay, that's not 1, has the logarithmic function f inverse of x equals log base b of x as its inverse, okay? And again, the diagram is down here. This will make it very clear, but if f of x equals 3 to the power of x, then f inverse is going to be log base 3 of x. Another example, f of x equals 1/4 to the power of x, then f inverse is log base 1/4 of x. And the key idea here is that the bases are exactly the same. Okay, so b to the power of x, it's log base b, and then inputs and outputs switch. Inputs and outputs. Okay, so if I have b to the power of x is equal to a, then my logarithm is going to be log base b of a is equal to x. Okay, inputs, outputs, switch. I can't say it enough. So let's go ahead and look at some examples. So here we're asked to complete the table by writing each of the given equations and its alternate form. So here I have 4 to the power of 3, 4 to the power of 3, 4 to the power of 3rd is equal to 64. So this is going to be log, okay, base is the same, 4, okay, and then the input, sometimes you'll see parentheses, sometimes not. I'm going to use parentheses here, of 64 is equal to 3. Inputs, outputs, switch. I would write that down. Okay, now if I have a logarithm base 81 of 3 is equal to 1/4, how can I write that as an exponential form? Well, again, base is the same. 81 to the power of, okay, well, inputs and outputs switch. So it's 81 to the power of 1/4 is equal to 3. Pretty easy, right? 2/3 to the power of p is equal to q. Well, as a logarithm, that's going to be log base 2/3 of q is equal to p. An important thing to remember, make sure that these logarithm values here, these are subscripts. So they're kind of like smaller than the rest of your writing, okay? So make sure you don't write it like super big. Okay, here I have log of 10,000 is equal to 4. And then here I want to let you know that this is what we call a common log. Common log. And with a common log, this is log base 10. Log base 10. So really there's an invisible 10 down here, okay? So we have base 10 to the power of 4 is equal to 10,000. All right. Okay, next, 5 to the power of -2 is equal to 1/25. Well, again, as a logarithm, this is log base 5 of inputs and outputs switch. 1/25 is equal to -2. Okay, and then I'm going to go ahead and introduce another logarithm. So I would highlight these. These are very, very important. The common log, and then we have here the natural log. Okay, and the natural log is log base e, which log base e we write as ln. Why is it ln if it's the natural log? Well, it's Latin for logarithmus naturale. Don't shoot me if I said that wrong. I don't speak Latin, but that's what it is. You can Google it. It's there, I promise. So this is log. Okay, base stays the same. E, inputs and outputs switch. So of 7.389 is equal to 2. Now I'm going to go ahead and I'm going to rewrite this. So we don't write log base e. I don't even want to say you can. What we write is we write ln. So ln of 7.389 is equal to 2. Well, not equal. I want to say approximately. Okay. So these are the two common logs, or the common log and the natural log. You'll commonly and naturally see them in mathematics. They're the most frequent ones that you'll see. All right, so I have some practice problems here. I would like you to go ahead and please try these on your own. Pause the video now, and I'll show you the solutions. Okay, so I'll assume that you have tried these. Here is the solutions. See if you got them right. All right, so that's it for this video. I have introduced logarithms, and we've talked about how to switch from exponential form to logarithmic form. That's an important kind of skill that you'll need going forward for the rest of Accelerated Math 3 as well as Calculus. And in the next videos, we're going to go ahead and talk about how we actually evaluate logarithms or solve kind of equations. All right, catch you next time. Peace. Hey there, welcome back. This is 9-1 and we are talking about logarithms. In this video, we are going to go ahead and talk about how you evaluate logarithms without a calculator. All right, so it is possible to write exponential forms with powers on both sides with the same base. Then we can utilize the exponential property of equality. So maybe you're asking yourself, what is the exponential property of equality? Good question. Well, here it is. The exponential property of equality states that if you have an equation where you have the base of an exponential expression on both sides, that's the same. Okay, so left side's equal to the right side, the base is the same, well then their exponents have to be the same, okay? And intuitively this kind of makes sense, right? And an example of this would be something like this. If I said 7 to the power of x is equal to 7 to the power of 2, what is x? You would say it's 2, right? Because the left side's equal to the right side, the base is the same. So we're going to go ahead and use this, and we are going to follow these steps, and we are going to rewrite the logarithm in exponential form. Use a variable to represent the logarithm's value. Okay, then what we'll do is we'll rewrite both sides of the equation so they have the same base. That's important. And in this lesson, we're going to use a lot of our exponential properties to go ahead and kind of manipulate our expressions. 3, use the exponential property of equality and then solve for the variable if necessary. Okay, and it's very, very important that you understand the variable's value is the value of the logarithm, and we write our conclusion. Okay, so here is the first example, and we have log base 4 of 16. So what we're going to go ahead and do is we're going to set this equal to x. Just set it equal to x, make it an equation, and then we'll switch to exponential form, right? So that was step 1, and then here's step 2. I'm going to rewrite it as exponential form. So 4 to the power of x is equal to 16. Okay, step 1, step 2. Next, I'm going to go ahead and I need to have both sides be the same base. Okay, so this is 4 to the power of x is equal to 4 to the power of 2. Okay, thus, here's where we use our exponential property of equality. I'm going to say, okay, x is equal to 2, and then we'll solve for x. Well, in this case, we don't have to solve. This is a foundational example, so we can write our conclusion. Log base 4 of 16 is equal to 2. And there's your answer. Example 2. I'll go ahead and set my logarithmic expression equal to a variable. It can be x, it can be y. I'll use y just to mess with your guys' heads a little bit. You're welcome. You're welcome. Okay, so now I'll go ahead and rewrite this as an exponential expression. So 5 to the power of y is equal to 1 over the power of 125. Okay, now I have to make both sides the same base. So just look at both sides and say, okay, what base family could I utilize? And hopefully 5 comes to your mind. 5 to the power of y is equal to 1 over 5 to the power of 3. Now, I want this to be, I want the 5 to be in the numerator. I want a base 5. So I'll use my negative exponent property. Okay, and thus we know using the exponential property of equality that y is equal to -3. Okay, so it's important, don't box y equals -3, right? You want to evaluate the logarithm. So we just used kind of a trick or a method to go ahead and evaluate this logarithm. So log base 5 of 1 over 125 is equal to -3. There you have it. That's it. Okay. Here are some practice problems. Please go ahead, pause the video. I want you to try these now. All right, so I'll assume that you have paused the video and tried these examples, and here are the solutions. Okay. Did you get them? Good job. Okay, so we'll go ahead and kind of ramp up our problems, make them a little bit more tricky. Again, you are welcome. So we have log base 36 of 6, and I'll set this equal to a variable. Next, I'll go ahead, I'll rewrite from logarithmic form to exponential form. So base 36 is 36, inputs and outputs switch. So 36 to the power of x is equal to 6. Okay, and now here, notice these are both family of 6s, right? Can't I rewrite 36? Whoa, can't I rewrite 36? Computer's freaking out on me. As 6 squared? Sure, okay. So this is 6 to the power of 2x is equal to 6 to the power of 1. And thus, here I can use the exponential property of equality. Say it, exponential property of equality. This says if left side is equal to right side, bases are the same, then exponents are the same. 2x is equal to 1. Go ahead, divide both sides by 2. Le dos, x is equal to 1/2. Are we done? No, rewrite your answer. Do we have to? Yes, yes. Yes, you do. Log base 36 of 6 is equal to 1/2. Ta-da! All right, not too bad. Okay, let's look at another example. We have log base 1/7. Log base 1/7. Who even uses that? Nobody, except these problems. Log base 1/7 of 49. I'll set this equal to y. So we have 1/7 to the power of y is equal to 49. I'm smelling family of 7s. Actually, I can't really smell right now. I'm kind of under the weather. I'm sick a little bit. I promise not to get you sick. That's why you're watching this video. So we have 7 to the power of -1 to the power of y is equal to 7 squared. Okay, so now I'll go ahead and use power of a power property, which says 7 to the power of -y is equal to 7 squared. And then I'm going to go ahead and use exponential property of equality. -y is equal to 2. So if we divide both sides by -1, we know y is equal to -2, which I always have to zoom out because I forget what the expression was. Log base 1/7 of 49 is equal to -2. All right, not so bad, right? Okay, so here is the next practice problems. Please go ahead and give these a try, pause the video, and I will assume you have paused. Here's the solutions. All right, so what I'm going to do, I'm going to go ahead and break apart. I'm going to split. I'll make this another video for the back half of the examples. All right, catch you next time. Hello, welcome back to the third video of 9-1, evaluating logarithms, and this video is going to focus on just some kind of tricky examples when we are evaluating logarithms. All right, so here I have log base 4 of 32, and we're asked to evaluate the logarithm without a calculator. So again, just go ahead, set the logarithm equal to a variable, and then rewrite in exponential form. So I have 4 to the power of x is equal to 32. And you have to ask yourself, okay, how can I make these both the same base? Now, all the examples that we've looked at first are kind of simplistic, right? I can just go ahead and set one side kind of equal to the same base as the other. So maybe you're thinking, okay, base 4. How can I write 32 as base 4? 4 to the power of 2 is 16. 4 cubed is 64. So you know you kind of blow past 32. So you cannot write both sides as base 4. So we need to kind of rethink. Well, I can go ahead, I can rewrite 32 as 2 to the power of 5. And can't I rewrite 4 as 2 squared? So rewriting both sides is sometimes a trick that you'll have to utilize. Okay, so this is 2 to the power of 2x is equal to 2 to the 5th. And the exponential property of equality says that 2x is equal to 5, so x is equal to 5/2. Okay, so our answer here log base 4 of 32 is equal to 5/2. All right. Okay, so here are some practice problems. Please go ahead, try these, and you'll have to use your math magic to rewrite both sides as the same base. Okay, hopefully you pause the video. Here is the solutions. Okay, the one on the left, you had to rewrite both as base 3, and the one on the right, base 4. Okay, so the last type of problems that you'll see when asked to evaluate logarithms is sometimes in function form. So here they say if f of x is equal to log base 1/2 of x, evaluate the following without a calculator. And what they give us is a function, f of 4. So all you do, right, is plug in your variable. So I have log base 1/2 of x, okay, and in my function I'm going to plug in 4. So what's log base 1/2 of 4? So I'll set this equal to a variable. I'm going to use y just to not confuse the variables here, and then I'll rewrite these both as exponential. So I have 1/2 to the power of y is equal to 4, and they need to be the same base. So what I'm going to do is I'll use base 2. So 2 to the negative first is equal to 2 squared. So 2 to the power of negative y is equal to 2 squared. So negative y is equal to 2. Thus y is equal to negative 2. Okay, so what that means is that f of 4 is equal to negative 2. There you have it. How about f of 2 root 2? And this one is going to be pretty tricky. So I have log base 1/2 of 2 root 2. Okay, so I want to evaluate this. I'm going to set this equal to y and then rewrite as exponential form. So 1/2 to the power of y is equal to 2 root 2. Okay, and now we have to go ahead and rewrite these both as the same base. And I hope you're thinking base 2. So on the left side, we'll use the same trick that we did in the first example. So 2 to the power of negative 1 to the power of y is equal to, and on this side what we're going to do, I'm going to rewrite this. This is 2 to the first, and instead of root 2, I'm going to rewrite this as 2 to the power of 1/2. Okay, well, I have power to a power on the left side, so that's 2 to the power of negative y, and on the right side, I am multiplying bases that are the same, so we add the exponents. Okay, so this is 2 to the power of, I'm going to rewrite 1 as 2 over 2, and I'm going to add 1/2 to it. So this gives us 2 to the power of negative y is equal to 2 to the power of 3/2. So negative y is equal to 3/2 by the exponential property of equality, and thus we know that y is equal to negative 3/2. Okay, so then f of 2 root 2 is equal to negative 3 over 2. No roots. All right, so that's it. That's how we evaluate logarithms. I have a couple of practice examples for you here, if you would like to try them. Okay, so definitely try the square root of 49. Try that one. And hopefully you've done that. Here is the solutions. And then one more set of practice problems if you're interested. Here you go. Okay, and then here are the solutions. All right, that is it. Catch you next time. Peace.